Thanks for choosing to listen to this Late Night Linux Family podcast. We're only able to do this because of the people who support us. None of our shows are paywalled, but our Patreon supporters can get most episodes early and never hear any ads. Learn more at latenightlinux.com/support or support us by telling a friend or colleague about everything we do. Hello and welcome to episode 150 of Linux Dev Time. I'm Joe.
I'm Amalith.
I'm Kevin.
And I'm Andy.
Good to talk to you all again. Andy, recently you've been thinking about what makes code fast.
Well, yeah, so I've been making a series of videos trying to do this thing called the 1 billion row challenge, which is a thing invented by someone in the Java world. But it's basically about how to do a task quickly. And that task is to read a 1 billion line text file and then summarize the information and print it out. And people have had real fun golfing that to make it go incredibly fast in Java and then in all the other languages because people got competitive about it. But so that's got me thinking about probably some quite misleading ways of thinking about how to make code fast, because most code isn't that, So I've been thinking about really low level stuff like how do I, remove one memory allocation? How do I do things without using ifs, because branching is slower than not branching when the CPU is executing it, and stuff that is really interesting to talk about, but it's probably not relevant to making most normal code fast. So I wanted to ask the question, what makes your code slow? What makes your code fast in your experience?
Well, I think if we take a step back or up a level or whatever direction that happens to be, when we say something is slow or it could be faster, I've always thought about it in terms of there's kind of two broad categories you can do. You can either do less. So something being slow means it's doing too much or doing something out of scope. So you can make it do less, or you could take better advantage of the hardware capabilities that you have. And those are kind of the two broad categories that I've thought of. When we say software is slow, we probably mean it's not doing one of those two things. Either it's just doing too much or it's not making good use of the hardware at hand. And there's all kinds of ways that fall out of those two categories. And there's probably others as well, but there's all kinds of ways that fall out of those two categories. But I think when we really think about it, that boils down to a lot of it, right? Even if you were to just think about something like finding a particular element in an array, and we were to say that the slow method would be kind of the brute force way where you just look at every single element and say is this the right thing? Yes or no. And then, either keep it or not. And then there's faster ways that we can do by storing it in different things B-tree maps or some other way, or hash maps. There's all kinds of ways that we can do this, but that is effectively just doing less. We've found ways to scope the amount of work we need to do to exactly what we want, and we do less, and therefore it becomes faster. So there's a lot of, I think, really cool things that fall out of that, that line of thinking.
Well, so an example of that from the billion row challenge that I've been working on is that in this text file, there's decimal numbers, but every single number is exactly the same format. So the first implementation I did was to use the built-in standard library number parsing to say, just parse this number. And I've honed that down and down to the point where the fact that I know exactly where the decimal point is going to be is critically important to the algorithm that I'm using. I know it only ever has one decimal place. In fact, it always has exactly one decimal place. So I now have this super fine-tuned algorithm for this very, very specific case, which is such fun stuff to do. And normally you don't get to do that, right? Because you always have to write your code in a sensible way that might come up from some different thing might happen later. So it's been nice to just take the kind of do less thing to the absolute extreme and just do exactly what is needed and no more for this very specific task.
Yeah, and you kind of touched on it there too, but there's always this constant tension between doing less or the very, very specific thing that is required for the task and the more general, what about if this thing happens? What about if I want to handle these cases? What if there's, more than one digit behind or in front of the decimal place, right? There's all kinds of things that are more general and therefore you do more. And with that, code becomes slower. And there's a bunch of different ways that this can happen as well. But I think it's a really good example of how there's a little bit of that tension between the more generality as well as the being very specific, doing less, going faster. I also wanted to pull up, there was something that you said earlier about how branching is slow. And when we talk about branching, a conditional value. So if there's a value of this, then we do this. If not, we do this other thing. So usually we think of them like an if statement, but there can be others as well. And when you do that, branching is in fact usually slow. There is kind of going back to that, making use of your hardware. There is hardware aspects where we can predict which branch we're going to go down, and called the branch predictor, very unimaginatively. And that hardware is usually really good about picking the correct branch. But if it's not, then there's a whole bunch of extra work that has to happen to like back up and then go down the correct branch. So this sort of like branching methodology is a spot that can come up in areas when you're doing a lot of profiling and trying to find out what's slow. Like branches often become the culprit. And something I heard a long time ago was that you want to push your ifs up and your loops down. And the thinking behind that is, if you're in your tightest, hottest path of code that happens billions or trillions of times, that's probably going to be like some looping aspect, and you want no conditionals in there. And if you can push all of your conditionals like up the tree or up the call stack or like to the highest part of the code, then all of that kind of slow branching happens well away from any of the like hot path where you can do a lot of things really, really quickly and, let the CPU like really rip through stuff. So that's another area where you can just take a little bit of methodology to make things, quicker by some dynamic or some method.
It's really fun and really interesting, this stuff. And it's really fun to golf your code to try and achieve these things. And what I found doing this challenge and trying to remove the branches and measuring, I was determined I was going to measure the results, because that's what I keep banging on about. Always got to measure your performance. And there was almost no difference between the branchy and the branchless code. And it actually depended which sample data I was using, which one came out faster. So I guess the branch predictor did a really good job on that code or something. I don't know. I think it reveals that I at least have absolutely no idea what the CPU is doing with my code. Like I have this vague idea that it can run lots of instructions simultaneously. So it kind of predicts what's going to happen next and tries to get ahead of you and do it for you. And if you make it hard to predict, that makes it hard for it to do that. But, that's as far as I go. And as I say, when I tried it out on this very tight optimization problem, it didn't come out at all how I expected. And I was very glad that I measured, but it's a lot of fun.
Yeah, there's, I guess, another degree of tension that happens with this sort of like optimizing thing. And that's like, how much time are you going to spend on it? And is that optimization worth it? And I agree, like doing this optimization stuff is something I really, really love doing. But there are times where you spend a ton of time on it, just like you were saying, like you go down to this like branchless methodology only to find out the code is possibly even slower than before, because modern compilers are very good. Modern branch predictors are very good. But you have to sometimes step back and say, like, is the work that I'm doing here worth it for the gains that I'm going to get? And if it turns out like you're just, let's say, loading the config file 20 milliseconds faster than you would have otherwise, and that config file is loaded once every 3 months, then it's probably not worth spending a bunch of time on that. So also asking yourself like whether or not this optimization stuff or like making the code faster right here really matters. And like, is that actually the hot path of the program you're running? And I would say often like loading config files is probably not where a lot of the time is spent, but for a very short-lived CLI or a program like that, maybe it is. But knowing where those hot paths are and whether or not your optimization journey is going to be worth it in the end is very important.
So, Amleth, I wanted to ask you, have you recently worked on some code where things were a bit slow and you needed to make them faster? And if so, like, why were they slow?
I have not recently, actually.
Well, does that imply something to us then, that maybe none of this really matters?
In the particular contexts in which I am writing code, it does not matter quite as much as in some other contexts.
So what do you think it is about that context?
I'm not sure. In our context, what we are doing is transforming messages from one protocol to another. And performance in that context is sensitive, but I think where the performance matters is not necessarily in the code we are writing. We have more picked libraries that take care of the performance-sensitive portions for us, such as parsing XML, for example. We are not writing any XML parsing. We picked a library for that.
Right, very, very sensible. Yeah, because I think that the places where performance becomes a problem is either when you need to do a lot of things or when you need to do something with a loss of data. So when your server becomes heavily loaded and you start running out of memory or CPU, that's when you start tuning it for performance, right?
I think it can also be when you want to minimize the amount of hardware required for a particular task. And like that can be, something could be perfectly fast or perfectly fine, but if the program is written in such a way that it requires extra memory, or maybe it keeps the CPU super busy or whatever it is, like that can be another reason to tune the performance and look at how you're doing things, even if like the speed is not necessarily the problem.
The memory thing surely is starting to come up with the price of memory being as ridiculous as it is now. Surely people are starting to optimize for that, or at least they should be.
Yeah, I think with the rise of cloud computing, I'm using extremely heavy air quotes there. Part of the thing that people said when that was coming along was people are going to start caring about this stuff much more because you pay by the CPU cycle or by the megabyte of RAM or whatever. So optimizing your code is going to immediately save you cash.
That worked out really well then, yeah?
I'm not sure it's really transformed into much of a change in the industry, to be honest. I thought it was interesting that, Amalith, you were saying that your code is like transforming strings, essentially, because one of the things that I had in my mind before we recorded this episode that I wanted to talk about was, in my experience, almost all programs are just moving strings from one place to another and converting them from one string format to another. And that's the 99% of the performance problems that you have to deal with. Like, oh, why aren't these strings just the same format? And we wouldn't have to do this.
I should also say that the code that I have been writing might not particularly affect performance because I have been maintaining code that someone else already wrote. They probably already thought about many of those performance concerns and maybe architected the application such that I don't have to think about that quite as much.
There's always a first time for everything, I guess.
There's also like the architecture is mostly static in some programs, right? But the requirements change over time. Hardware changes, constraints change, all kinds of things change, but unless you actively change the architecture, it's going to remain the same. So there's probably more opportunity to look at like an architectural type thing. And this kind of goes back to the like doing less, right? So if there's a different way to do what your program is doing, but in a more finely tuned way that does exactly what you need, like that, those are sometimes ways where you can get wins as well without even having to look like the really low level performance stuff.
I remember a particular time when an architectural constraint caused us massive performance problems. We were making a UI app that did some clever businessy thing, and we were forced without any choice from us that we had to implement it within a particular framework that had been developed by another team. And we also had to embed some of their kind of widgets that they developed in that framework as well. And our code operated outside of where they expected all the work to be done. And so we ended up essentially, obviously it was a massive, massive blob of XML, because everything is, or was at that point anyway. And then we had to take a little chunk of that XML, try and find a coherent chunk of that XML and give it to this widget, because the widget couldn't handle the large size of XML that we were actually dealing with. So a lot of my time and effort went into A, figuring out how to break our model into coherent pieces that we could give to this UI thing, and B, trying to make that not take like 30 seconds of just copying strings from one bit of memory in one Unicode encoding to another bit of memory in a different Unicode encoding. It was great fun.
That actually makes me think of one of those categories of like using your hardware better. But a lot of programmers, I would say, are not the greatest at using all of their hardware, right? And this maybe is a somewhat of a hot take, but for example, like a lot of code is written in like a single threaded method, either because that's the constraint that was given, right? Like maybe it's the algorithm or whatever is not, or the data is not amenable to being multi-threaded or using multiple cores. But I would say more often than not, like there is the ability to use that hardware a little bit better. And the single threaded approach is kind of like the most naive or most direct approach. And that's what a lot of people do. And so you end up having possibly a single thread, just like ripping through stuff. Meanwhile, your other 3 to 15 to 31, however many other cores you have might sit mostly idle or just doing like OS or background tasks. So like, I wonder too, if you were to look at some of those like sort of string processing type things, right? Like those are oftentimes very amenable to like, hey, what if we just like pass this out to the various threads and like let each one of them rip through some of this data, and you can get like massive wins in, I would say, relatively short order.
Yeah, although I think the ideal is just not to be transforming massive blobs of text into another blob of text that means exactly the same thing. But, you know, sometimes you have to do these things.
Well, yeah, I mean, I would say that's more on the like architectural side. If we can not have to do that, that's excellent. That's doing way less.
So speaking of like using your hardware effectively, last night I was playing again for another bit of this billion row challenge with SIMD, which is something I haven't used before. I think that's how you pronounce it, SIMD. So that's a feature of modern CPUs, actually not even that modern, it's been around for ages, but which effectively allows you to do arithmetic with like up to 64 numbers simultaneously, and takes a single CPU instruction to do the same thing to 64 different things at the same time. And it's so cool. If you construct your algorithm to make use of it, it's like magic. It's just like 64 times faster.
Yeah, SIMD is one of those like, I think of it as like an arcane magic kind of thing. So SIMD is the single instruction, multiple data, and other like ARM I think has something called Neon that's very similar. But the idea of it is, if your computer can do a single instruction on like one bit of data, or not like bit in the memory sense, but like one piece of data, or it can do that same operation across multiple bits of data that are the same with a single instruction. And so the SIMD is like a really, really cool way to get these like big speed ups when you're doing processing like that. I think most modern compilers also have ways to do something called auto-vectorization, which will do this in the background for you. So if it notices a pattern that is amenable to SIMD, it can transform, a particular loop to utilize these SIMD registers. So these are like special registers on the CPU that are bigger than the normal kind of general purpose registers. And it'll utilize those to get through the data faster. So if you see things where you're compiling with different CPU features or checking CPU features like SSE or AVX, things like that, those are those like SIMD registers and instructions. And so modern compilers are pretty good about doing that, but they're not great. Like it's pretty fragile, and relying on something like auto-vectorization in my experience has not been super great. And looking to make sure that the code actually is using that type of instruction set, and if not, doing so manually, you can get some pretty big wins. But then much like everything in computer programming, you also have to monitor that, because you might go through this whole process to, vectorize something yourself and use these SIMD registers, only to find out that like later on, that was actually slower than if you had just like done the naive thing and the compiler could have noticed it and done something different anyways. So it's something you also have to like constantly look at.
Yeah, or you just have to run it on ARM, and you've implemented it all on x86, and now none of it works, and you're back to the bad old days when you had had problems like that. But yeah, it was great fun. It made me feel like a ninja, and it did actually, in the thing I was doing, once I got it right. Well, I got it wrong first, and it was slower, but once I got it right, it was faster than the thing I was doing before, which made me feel so good. But yeah, you would hope between the specialized libraries or standard library and the compiler, you wouldn't have to think about that stuff too often in your normal work.
Andy, are there also other areas in this billion row challenge? Like, I guess, what have you found was like the most either difficult thing that you struggled with, or maybe even like what were some of the easy wins initially? Because like I'm imagining, a billion rows, you're not going to read like the entire file into memory at once, right? So I'm assuming you have to do some sort of streaming thing. But I guess what were some of the initial approaches that you took, and some of the early wins, I guess?
That's right, yeah. So there were definitely areas that felt much more natural to me. So the one I had the most fun with was parsing these numbers, because I love writing parsers, and it felt like something I was already familiar with. And then some areas were much less familiar to me. So by far the hardest thing that I've done so far, and I haven't done the bit, there's going to be a bit where I have to make a hash map to summarize that data as it's coming in without storing the entire file. So the hash map will be interesting and quite challenging. But the bit that's been challenging to me so far, and probably is going to be the hardest bit of the whole project, I think, is just getting the bytes out of one place into another, right? So I've been using a memory map to do that, which is like a Linux kernel feature, where it makes a file on disk look like it's a piece of memory, which like is a kind of a neat feature. But the thing that's happening underneath is the kernel's also hopefully making it quite fast to access those bits of what look like memory, because it can read ahead and predict where you're going to read in the file, and just the kernel is closer to what you're doing, so it has an opportunity to do things nice and fast if you use a memory map. But even then, I was disappointed that didn't give me as much of a speed up as I expected over just reading a file directly in chunks, but it did give me a small speed up to do that. But yeah, just getting the bytes out and then doing even a minimal thing with them, when there's a billion rows, it's a big file, takes an awful long time.
You said also that you have to write a hash map. Are you writing a hash map from scratch? And if so, why?
No, I won't. Well, I might try writing a hash map from scratch just for fun. But my anticipation, having watched other people attempt this challenge, is that the built-in hash maps in Rust are more than adequate, way better than I could write. But the hash function that actually hashes individual items and turns a thing into a number that can then be used by the hash map. The hash functions that are used in standard Rust are like really smart and useful and flexible and potentially cryptographically secure in certain contexts. And so I'll be looking for something like super dumb and much quicker and less flexible than that.
Luckily, Rust does have good support for swapping out the hash function there, and there are ones that are much faster than the default one, which like you said, is cryptographically secure. So it's much slower, but then much more secure in some contexts.
I think something that is really important for good performance from hash maps is to think about, first of all, how much time are you spending building the map and how much time are you spending just looking things up in the map when the index is already built, like you've got all the keys already there. And in this case, in this challenge, it's definitely the second part that's going to be the majority of the time. You've got all the keys already because there's a huge number of rows and there's only a limited number of possible keys that you'll have. So then how to make the performance of looking up keys in a map that already has all of its keys, just looking up and making small updates to the data in there, as opposed to the time when you're building the hash map up from nothing, which is less important in this challenge, but could be important in your use case. But then the other part of it is how often do hashes clash with each other? So the ideal way a hash map works is that there are no clashes. So every single key hashes to a completely separate number, and then you don't have to waste any time deciding which one of the keys you've actually got to when you end up in that bucket, as it's called. So I'm going to do a bit of statistics on the keys in the example that I've got to try and figure out what hash function I can write that has as few clashes as possible, but is still really fast to run. And that'll be sort of interesting, I think.
Well, I think you mentioned it there as well briefly, but it can also be like, what are you going to do once you've loaded the data into memory? Because there are certain types of, not just hash maps, but like other data structures as well, which have similar interfaces to a hash map. But let's say, for example, you wanted to iterate over all the keys, can be much faster than iterating over all the keys in a standard hash map. Mm-hmm. So depending on like what you want to do frequently and what you need to do really quickly, that can also kind of change the approach for the hash map or whatever type of map you end up settling on.
Definitely. Like this challenge, I've become convinced from looking at what other people have done, hash map is boringly going to be the right answer. But yeah, there's all kinds of data structures that, depending where you're spending your time, if you're spending more of your time reading out from it, or you need things to come out in a particular order, you might want like a heap or something like that. You might want to try, if that's maybe how you pronounce it, or all kinds of other cool data structures, or just some kind of B-tree map. But in the case of most of the runtime, all the keys are there, and you just need to go in, modify the thing on the right-hand side, and come out again. And then the actual like reading out at the end is a tiny amount of the runtime compared with that stuff. I'm pretty sure, boringly, a hash map is going to be the right answer.
Have you had to look at stuff like cache size or like the data going through caches? Have you had to look at that sort of stuff for this challenge?
I've thought a bit about how the kernel is caching the file, but I haven't thought much about like, can I fit the stuff into the cache, because I'm kind of constrained about what data I'm using is going to be. It's a kind of fixed size. I definitely think the question of how big do you want the hash map to be to avoid clashes, but to not take up too much memory and potentially blow your cache is going to be interesting when we get to the hash map bit.
Interesting. Yeah, that's an area that I've found is particularly tricky to work in. And it's one that I also find like super interesting if you can make it work right and really care about like, and this is not necessarily for your, like the billion row challenge. This is more of generalized things that I've struggled with, is like trying to get data structures or pieces of data the right size so that they're cache friendly, and then make sure that they have some sort of like memory locality so that the like memory prefetcher can pull these things readily and you're not evicting other caches, which also becomes more important when you're using multiple cores too. So that is another area that like has all kinds of rabbit holes that you could dig down into.
I feel like the impression that we're giving to someone, if they're not following everything we're saying, is that there's a ton of stuff to know and it's all a bit scary. But I think the impression you should get is it's incredibly fun, and learning about it is like, I just think it's really cool to take a piece of code that already works and make it work exactly the same, but way faster. It just makes me feel so good.
Yeah. And that's why if we go all the way back to the beginning, those kind of like two axes of doing less or doing something, more finely tuned, or using your hardware more efficiently, like you can do that at any layer of the stack. You can do that like not down at the CPU cache and SIMD register. Like you don't have to be down at that level to care about like, oh, am I doing more than I need to for this task? Or do I have more hardware I could utilize in a better way? Am I using it efficiently? Like you can do that all the way at the very top level of programming and make measurable differences to your programs.
Something that a friend likes to say is try to be aware of what the computer is doing with the code you're writing pretty much all the time, not just when you're optimizing something that's slow.
And then we haven't even really talked on it, but human perception is a massive part of this.
Yeah.
And your computer can be very fast, doing the most efficient thing, the most finely tuned thing. But if you are not responsive to the user, if this is a user-facing application, it can seem really slow. So like that's a whole other side of this coin that we haven't even touched on.
The other way around too. Your program can be slow and rubbish, but if you put a nice UI over it so that when you click a button, it actually clicks, then the user's going to think it's nice and fast.
Yeah, like how I turn animations off on Android.
Yep, me too.
And it feels so much quicker, even though it's not.
But then you're missing out on the pretty animations.
That makes me feel good. Every time I see the static circle sitting on my Android screen that's not spinning, I get this little moment of, oh, thank goodness I'm not wasting my time looking at a spinning circle.
That's usually like when I'm trying to do something faster or try to optimize something. I'm always like what else is the OS doing that I just don't care about right now? And it's probably something like making some little icon spin in a circle or something. Like who knows?
Yeah, there was some interesting work a few years ago about power saving, and it was less about doing less computing and more about allowing the computer to be asleep for longer by having just long periods when absolutely nothing is happening so the CPU doesn't have to wake up. So any program that wakes up and like checks something every few milliseconds is just terrible for your power consumption.
I mean, that's a big part of the doing less. If you run less instructions, you will use less battery for devices that have a battery, but also like just less power draw. Or there is the argument that if you use the hardware more efficiently and do something really quickly and then spin down to nothing, that is also more efficient power-wise for either battery or just power draw. So like there's advantages to this outside of just like make the thing go faster.
I'm currently writing a game and it wakes up every few seconds or so. I can't remember how long. Anyway, it wakes up every so often and decides whether it needs to save the state to disk. And I just feel really guilty about that now because now I'm thinking about, oh, it's going to wake up and do some work and then use some power. But I don't know. Sometimes at some point your program has to do the thing it's supposed to do. So you have to do it.
I was thinking about something like that recently with a spin lock, where I just feel terrible doing nothing and waiting for a second before coming back to check a lock. And I'm like, this feels so inefficient. However, like it actually is not bad in the grand scheme of things. But yes, those types of feelings is not fun as a developer when you're like, man, I'm just doing nothing right now.
Well, unfortunately, we've gone too slow with this and run out of time. So we'll have to return to it another day. We'll be back in a couple of weeks. But until then, I've been Joe.
I've been Amalith.
I've been Kevin.
And I've been Andy.
See you later.